Good morning students. Now we are dealing with our next chapter, that is electrochemistry. Electrochemistry is a branch of chemistry which deal with the electrical and chemical changes. That is, we can say the branch of science which deal with the electrical and chemical energy is known as electrochemistry. In this chapter, firstly we have to study about galvanic cell. Galvanic cell is also known as Daniell cell or voltaic cell. In this condition of you have a zinc is dipped in the zinc sulfate and copper is dipped in the copper sulfate solution. So they are connected by a salt bridge. Salt bridge is made up of agar or KCl. So you already know, you have to know the reactivity series. I'm written here a simple structure of the reactivity series. So the reactivity series, down the group the reactivity decreases and upper side the reactivity increases. Therefore we can say that the potassium is highly reactive than that of the bottom element. That is, if you immerse a little bit of sodium into water, sodium will be react with a very high energy, but gold, even though if it is react with water or steam, it does not react. That of the reactivity of gold is comparatively is very low. So this is the reactivity series. So here I am given is zinc and copper. So check where is here is a zinc and here it is a copper. The top one will be anode and bottom will be cathode is the condition. The top one will be act as the anode and the bottom one will be act as a cathode. So anode undergo oxidation and cathode undergo reduction. So you have to know the reaction at the anode, that is Zn will undergo oxidation, that is Zn gives Zn2 plus 2 electron, and at the cathode the reduction occur, that is Cu2 plus 2 electron will give Cu. First in the anode, that is Zn gives Zn2 plus 2 electron. In the case of Cu, that will become Cu2 plus 2 electron, it will give Cu. Is that clear? So we studied the reaction to anode and the cathode. See here guys, so now we already know the reaction to anode and the reaction to cathode. So we are calculating the overall reaction. The overall reaction will be equal to the 2 electron will be cut off. Then you have to add the reaction to the left side, that is Zn plus Cu2 plus will give Zn2 plus Cu. This is the reaction. For the cell representation, I am giving a simple method. You can use ABC model of cell representation. You have to know what is meant by ABC model. ABC model is anode bridge cathode is a reaction. Anode bridge cathode is the cell representation. So first of all you have to know about the anode, that is Zn changes into Zn2 plus, that is Zn bar Zn2 plus. Then bridge is double bond. Then cathode is Zn gives cathode is Cu2 plus gives Cu. Cu2 plus will give Cu. Is that clear? This is the cell representation. Is that clear? So now we studied the reaction at anode, reaction at cathode, and now we studied the overall reaction and how to form the cell representation. That is anode bridge is double bond, double line. Then we form the cathode. Is that clear? Now you have to know this point very well, that is the electron flow will be always from the anode to cathode, while the current flow will be opposite, that from the cathode to anode. Electron flow is from anode to cathode, but the current flow will be from cathode to anode is the condition. Is that clear? Now we have to study what is the measurement of electropotential. We don't know the electropotential of, for example, if any other element are given, we don't know the zinc electropotential, we don't know. Copper, the electropotential we don't know, that is minus 0.76 or plus something, any point, we don't know current value. To find the electropotential of a particular element, we have to connect it with She. What is She? Standard hydrogen electrode. She is known as a standard hydrogen electrode. Is that clear? What is She? Is a platinum wire coated with a platinum black in a 1 molar acidic solution is the condition of a She, that is standard hydrogen electrode. What is the condition? Platinum wire coated with a platinum black in 1 molar solution is the condition of She, that is standard hydrogen electrode. In this standard hydrogen electrode, this is the cell representation you can do, that is platinum bar H2 bar H plus, platinum bar H2 bar H plus. This is the cell representation. Now it's clear. Now we deal with the chapter, that is electrochemistry. First of all, you have to know what is meant by electrochemistry. Electrochemistry is a branch of science which deals with the electrical and chemical energy. Then we studied about galvanic cell or Daniell cell or voltaic cell, where you study the anode and cathode, that is zinc and copper. So the zinc is in the topmost position in the electrochemical series, therefore it has as an anode, and the bottom one will be act as a cathode. So anode will undergo oxidation and cathode will undergo reduction. So now you have to know the reaction at anode, that is Zn gives Zn2 plus 2 electron. Cathode, the reaction gives Cu2 plus 2 electron will give Cu. Now you have to know the overall reaction, and cell representation is based on ABC model, that is anode bridge cathode. that is Zn bar Zn2 plus double bar Cu bar Cu2 plus. Now you have to do the electron flow is from anode to cathode, but the current flow is from cathode to anode. Is that clear? Now for the measurement of the electropotential, we have to use She. What is meant by She? Standard hydrogen electrode, that is platinum wire coated with a platinum black in 1 molar solution. So the cell representation of She is platinum solid bar H2 gas bar H2 aqueous. This is the condition of this cell representation. Now we are dealing with the next equation, that is Nernst equation. It's very important to study the Nernst equation and the problem related to Nernst equation. So in this Nernst equation, we already know that E cell is equal to, I am not writing E cell, I am writing only E here. E cell is equal to E0 cell minus 2.303 RT by NF log. It is M divided by M N plus, that is in aqueous solution, that is here M, the concentration of M is equal to 1. That is 1 divided by concentration of Mn plus ions. Is that clear? So E cell is equal to E0 cell minus 2.303 RT by NF log 1 by M raised to N plus 1. This is the equation, where R is known as the 8.31 for universal gas constant. T is the temperature at 273 Kelvin or 298 Kelvin we are taken. Then F is the Faraday's constant in coulombs, that is 96500 coulomb. Then we can write this equation, the same equation in this form, that is E cell is equal to E0 cell minus 0.0591 divided by N log 1 by Mn plus. Or commonly we can say E cell is equal to E0 cell minus 0.0591 divided by N log this component that is reduced divided by the component that is get oxidized, that is reduced state divided by oxidized state. These are the basic 3 equations I am given here for Nernst equation. So in the condition of Nernst equation, you have to keep it in your mind, that is E cell is equal to E0 cell minus 2.303 RT by NF log 1 by Mn plus in aqueous solution. And if here 1 F is equal to 96500 and this R is equal to 8.314 joule K inverse mole inverse. Therefore E cell is equal to E0 cell minus 0.0591 divided by N log 1 by Mn plus ions. So we can say this is component as reduced divided by oxidized. Is that clear? Then here, what are the applications of the Nernst equation? Consider the equation AA plus BB gives CC plus DD. We can write the equilibrium constant Kc is equal to concentration of C raised to C into concentration of D raised to D divided by concentration of A raised to A into concentration of B raised to B. This is the equilibrium constant, that is Kc. Okay, with respect to concentration. Therefore E cell is equal to E0 cell minus 0.0591 divided by N into, we can write like log concentration of C raised to C into concentration of D raised to D divided by concentration of A raised to A into concentration of B raised to B. Instead of this writing this, I am writing in log Kc. Is that clear? See here, at equilibrium this E cell is equal to 0. At equilibrium we can write E cell is equal to 0. Therefore E naught cell, that is E naught cell is equal to 0.0591 divided by N log Kc. From this value you can find the Kc, that is equilibrium constant with respect to concentration. Is that clear? So what all things we studied here? We first of all in this chapter we studied what is the galvanic cell, or what is the anode, what is the cathode, what is the electrochemical series, what is the cell representation, and we studied with the Nernst equation the cell, that is E cell is equal to E0 cell minus 2.303 RT by NF log 1 by Mn plus ions. So we can say where F is equal to 96500 coulomb, or R is equal to 8.314 joule K inverse mole inverse, where E is equal to, we can also write, we are computing these all equations, we get E is equal to E0 cell minus 0.0591 divided by N log 1 by Mn plus, we can also say that it's reduced divided by oxidized. Then we have 2 applications of the Nernst equations. If it is used to find that that is E cell with respect to equilibrium constant Kc, or we can find the equilibrium constant Kc itself. And we can find the relationship between the Gibbs energy and this E cell. We can write that is standard Gibbs energy delta G0 is equal to minus NFE. Minus NFE, where E is equal to E0 cell, or we can say delta G0 is equal to 2.303 RT log Kc. RT log Kc. Keep these equations with your mind. We need this equation to do the problems, and we can go to the next. Now we are dealing with some of the equations related to our chapter. So first of all, we are dealing with the conductance condition. In the conductions, I am given your table, that is equations, that is conductance, specific conductance, equivalent conductivity, and molar conductivity. So from this table itself, you will get it. What is conductance? Conductance is represented by this symbol G, where the formula, this conductance is equal to inverse, that is inversely proportional to resistance, that is 1 by R. So the unit is ohm inverse or Siemens. The specific conductance, that is kappa, that is K, or conductivity, is equal to 1 by rho, or we can say GL by A. The unit is ohm inverse, centimeter inverse, or Siemens meter inverse. Equivalent conductivity, that is lambda equivalence, is equal to kappa into V, or kappa into V is equal to 1000 divided by N. So we can use the code, that is ohm inverse centimeter square G equivalent inverse, or SM square G equivalent inverse. Then we are given another equation, that is molar conductivity, lambda M is equal to kV, that is equal to K into 1000 divided by M, that is M is molarity. In the above, that is equivalent conductance, that is normality. In molar conductivity, we are using molarity, that is lambda inverse, that is M centimeter square mole inverse. Okay, or you can use a Siemens meter square mole inverse. These are the equations related to conductance. Then you can search the equations related to resistivity conditions and equations. Resistivity is represented by kappa, and their conditions related to that. Then after that, I am giving you a graph related to this conductivity or molar conductivity. That is, and molar conductivity, and what is meant by limiting molar conductivity? When molar conductivity approaches to 0, that is known as a limiting molar conductivity. I am giving a graph with respect to concentration and molar conductivity. That is, I am giving you a graph that is having strong electrolyte and the condition of weak electrolyte. Go through this graph and study the graph very well. So we are now discussing about the conductivity and molar conductivity. The molar conductivity, that equations, that conductance, the equation is G, that is inversely proportional to resistance. Then specific conductivity kappa is 1 by rho, then that is inversely proportional to conductivity, or we can say equivalent conductivity, that is K into V. Molar conductivity is K into V, where is K into 1000 divided by M, but in equivalent it is K into 1000 divided by N. Then go through the effect of dilution, that is conductance increased as number of ions are produced. Specific conductivity decreases with the dilution, and equivalent conductance increases with the dilution, and molar conductivity increases with the dilution due to large increase in V, and both are same, that is increase in dilution with a large increase in volume, and both equivalent conductance and molar conductivity both are same, they are increased by large increase in their volume. Then we discussed about the molar conductivity and limiting molar conductivity. When the molar conductivity approaches to 0 is known as the limiting molar conductivity. I gave you a graph between root of C and M, where you can see the straight line which is regarded as a strong electrolyte like KCl, and the curved one which is considered as that is ethanoic acid, that is considered as a weak acid or weak electrolyte. So go through this topic and study the topic. Students, now we are dealing with the Corrosion law. Corrosion law is, we already know, it is the sum of the that is cation and anions, but that is the sum of the cation and anion of infinite dilution of a molar conductivity is known as the Corrosion law. We can also say that equivalent conductivity will be equal to the sum of the ionic conductivity of cation and anion, or it will be cancelled. Also say that the molar conductivity on infinite dilution will be equal to the sum of the cation and anion is regarded as the Corrosion law. For example, if we have to find the molar conductivity of NaCl, you have to find the equivalent conductivity, that is with respect to the conductivity of that is anion, that is Na plus, and the conductivity of Cl minus. Is that clear? We will find the conductivity of Na plus and the conductivity of Cl minus. Is that clear? Now see here guys, what we are going to discuss about what are the applications of the Corrosion law. The first application, it is used for the calculation of the molar conductivity of weak electrolyte. Okay, that is, for example, ethanoic acid, it is used to find the molar conductivity of weak electrolyte like ethanoic acid, some like the compound that will be shows a negative, that is curved structure, that is curved graph in the graph between molality and the root of C. And also it is used for the calculate the degree of dissociation alpha, that is molar conductivity of the concentration divided by molar conductivity on infinite dilution, that is alpha. Alpha is equal to that is is molar conductivity of the concentration divided by molar conductivity on infinite dilution, that is lambda mc divided by lambda m naught. Then we can find the calculation of dissociation constant, that is Kc. The dissociation constant, the equilibrium constant is considered as Kc. Here you can use the dissociation constant as K or any other value K. So you can use K is equal to C alpha square divided by 1 minus alpha square, that we are studying the chapter equilibrium. Then you have to find the determination of the ionic product of water. For this you have to study this one. This was the molar conductivity of water is equal to, that is lambda H plus the lambda OH minus. We can also say that the molar conductivity is equal to K into 1000 divided by molarity, that we already discussed. If it is molar, that is conductivity. If it is equivalent conductivity, it will be divided by normality. So here it is, if it is molarity, K into 1000 divided by molar conductivity of H2O. So we can use that 10 into 1000 divided by molar conductivity of H plus the molar conductivity of OH minus. Here see, so we got the value of here the molar conductivity of H plus I am given here, it is 349.8 S Siemens square in mole inverse, and the molar conductivity, that is lambda OH minus is equal to 198.5 S Siemens square mole inverse. So you got the molarity is equal to 1.01 into 10 raised to minus 7 gram ion liter inverse. Then you have to find the ionic product of water, that is Kw. To find the ionic product of water, you have to find this Kw is equal to H plus into OH minus. You got a value 1.02, that is H plus we have this molarity and OH minus will have the same molarity. It will become 1.02 into 10 raised to minus 14, that is adding these values you will get that 1.02 into 10 raised to minus 14 is the ionic product of water. So what is the first application? The first application, it is used to find the calculation of molar conductivity of weak electrolyte, and also it is used to find the degree of dissociation, that is alpha is equal to lambda mc divided by lambda m naught. It is used for the calculation of a dissociation constant Kc, that is C alpha square divided by 1 minus alpha, and it is also used to find the ionic product of water. Also it is used for the determination of the solubility of sparingly soluble salt, that is solubility is equal to K into 1000 divided by cation plus anion is the condition. So these are the made by corrosion law and the applications of corrosion law. So now we are going for the next topic, that is the electrolysis and the different types of batteries. Now we are going to discuss. Okay, let us look. Students, next we are dealing with electrolysis. I'm given the text that is electrolysis. We are discussing with the Faraday's first law and the Faraday's second law. So Faraday's law of electrolysis, the first law we are given, it is the mass of any substance deposited or liberated at any electrode will be directly proportional to the quantity of electricity passed. So we can say that W is directly proportional to Q, that is W is equal to Z into Q, where Z is the electrochemical equivalent substance deposited, that is Z is equal to equivalent weight of the substance divided by that 1 farad, that is 96500. So we can use the equation, that is W is equal to ZIT will be the final equation. So go through the Faraday's first law very clearly. The mass of any substance deposited or liberated at the electrode is directly proportional to the quantity of electricity passed through the electrolyte, or it may be a solution or in a molten state. Then we are going to the Faraday's second law. The amount of different substance liberated by the same quantity of electricity passing through the electrolytic solution will be proportional to equivalent weight, that is W1 by W2 will be equal to E1 divided by E2, where E is the equivalent weight. So now we discussed about Faraday's first law and Faraday's second law. First law is W is equal to ZIT, that is the deposited mass will be directly proportional to the quantity of electricity passed, and second law, that is the mass deposited will be proportional to equivalent weight. These go through these two equations, study that two equations very well, because based on this equation we have to go through some numericals. Then below that, after that I am giving you a table that related to the reactions at anode and cathode with the molten NaCl, aqueous NaCl, dilute H2SO4 and concentrated H2SO4. So molten NaCl, that is at anode or cathode, the condition is given. At the cathode, sodium will be liberated. If it is aqueous, the hydrogen will be liberated at cathode. If it is dilute H2SO4, hydrogen will be liberated cathode. If it is concentrated H2SO4, hydrogen is liberated cathode. If it is molten NaCl, chlorine will be liberated anode. Aqueous NaCl, chlorine will be liberated anode. Like it is negative will be go to the negative one, that is anode. sorry, positive 1 anode. Then dilute H2SO4, oxygen will be liberated at anode, and concentrated H2SO4, that is H2O8 minus, will be liberated at anode. So I'm giving the reactions at anode and cathode. Go through this reaction and study this whole reaction. So now we discussed about the electrolysis, that is with respect to the passage of electricity. We discussed about the Faraday's first law, that is the total weight liberated will be directly proportional to quantity of current passed, that is W is equal to ZIT, that is Z is equal to equivalent weight of the substance divided by 96500. Then we studied that the second law, that is the weight deposited will be directly proportional to the equivalent weight, that is W1 by W2 will be equal to E1 by E2. So we are going that will convert that chemical energy into electrical energy. There are primary battery and there are secondary battery, and also we are discussing about the fuel cell. For the primary battery that is not rechargeable, that can be only used for the first time. Example, that is Leclanche cell or mercury cell, that is dry cell or mercury cell. Then secondary battery, there are rechargeable batteries that they have infinite charging and discharging. Examples is lead storage battery and nickel cadmium cell. Then we are also discussing about fuel cell. It is a galvanic cell which will convert chemical energy of fuel into electrical energy, that is chemical energy into electrical energy. It is a type of a galvanic cell. Example, we are discussing about H2O2 fuel cell. This is the most efficient and pollution free fuel cell we are discussing. So first of all, dealing with the dry cell, the reaction at anode, that is I'm given your table, that is Zn gives Zn2 plus 2 electron. Then cathode reaction, that is MnO2 plus 2 NH4 plus 2 electron gives the Mn2O3 plus 2 NH3 plus H2O. Then second one is mercury cell, that is mercury cell, it is mercury cathode and carbon anode. So mercury we are using Zn plus 2 OH minus, use ZnO plus H2O plus 2 electron. Then cathode reaction is HgO plus H2O plus 2 electron gives Hg plus 2 OH minus. So we are discussing it as a mercury cathode and mercury, that is we are using mercury cell, we are having carbon anode and mercury cathode, carbon anode and mercury cathode. Then we are going for lead storage battery that having a lead at anode, that is, and that is reaction at anode is Pb plus SO4 2 minus gives a PbSO4 plus 2 electron, and the reaction at cathode is PbO2 that plus SO4 2 minus plus 4H plus 2 electron gives PbSO4 plus 2 H2O. Then we are dealing with nickel cadmium cell, that is cadmium plus 2 OH minus will gives CdOH twice plus 2 electron, and the cathode reaction is NiO2 plus 2 H2O plus 2 electron gives NiOH twice plus 2 OH minus. So all this reaction, go through this all the reaction of a dry cell, mercury cell, lead storage cell and nickel cadmium cell, and also try to find the overall reaction by calculating the addition of overall reaction of anode and cathode. Then we are discussing about the fuel cell. It is a galvanic cell which will convert the chemical energy of a fuel into electrical energy. Example, we are discussing H2O2 fuel cell, that is 2H2 plus 4 OH minus will give 4 H2O plus 4 electron, and the cathode reaction is O2 plus 2 H2O plus 4 electron gives 4 OH minus. Go through that reaction very well, study this topic very well and make it clear. And so students, now we are dealing with corrosion. Actually corrosion is the oxidation of metals. So it is, we can say that a rusting of iron is an example of corrosion of iron, that is Fe become Fe2 plus at anode, and cathode, that is O2 plus 4 OH plus 4 electron become water. Then you have to find the overall reaction that I am given in the board itself. Then how can we prevent corrosion? That's the important thing. That is we have that is coating of paint, or it can be using making of alloy, or galvanizing. In any method we can use to reduce the corrosion. So go to the topics, that is what is meant by corrosion, that is oxidation of metal ions. So first of all, we discussed about corrosion of iron, that is rusting. It is electrochemical phenomena which occur in the presence of moisture and oxygen. So that is the reaction at anode, that is become anode oxidation, that is Fe gives Fe2 plus 2 electron. The cathode, O2 plus 4 OH plus 4 electron gives 2 H2O. Then you have to find the overall reaction. Then go through the methods that is used for the prevention of the corrosion. That can be painting or making of alloy or galvanizing, any method you can use to reduce the corrosion. So go through the topics, and we can also say that the rusting of iron will come brown in color, and the green color in the copper is also type of a corrosion, and the black color in the silver is also another type of corrosion. Underline that is green color in copper and black color in that is silver. That is the silver get black, this is type of corrosion, and the copper getting green in color in their surfaces, this is due to corrosion. So go through the topics and underline that and make a note of these all things, and we can discuss the class discussion in our class in our live sections. Okay.
Bright Education Center, Medical and Engineering Entrance Coaching Center, Hilal area, Doha, Qatar. For further enquiries, contact 306000679.